So I just started writing some of the stuff from last class just to get us refocused. Today we're going to talk about a very particular type of neural network called a convolutional neural network, which we just started talking about at the end of last class. So just as a reminder, remember how in convolutional layers, which we started talking about, we have a kernel that's applied across the image, and we take the dot product across each patch of the image. That gives us a new pixel value for the corresponding next pixel, or corresponding pixel in the next layer. And we could kind of see this visually from this depiction. And we said the two key ideas. One, several kernels, which will allow us to extract many different kinds of features. Each kernel extracts different kinds of features, but instead of being features that we pre-specify, they're features that are learned to be the best features to extract. Novel idea. And the second key idea is that we will learn, I guess I already said this, but learn the best kernels, and we learn the kernels. So the main layer, or I should say the main new layer for a convolutional neural network is called a convolutional layer. And we're going to start learning about all different types of neural network layers and how they can all be mixed and matched to eventually create something like ChatGPT, which we will get to. And so for in a convolutional layer, we have our input image for now, which I drew above, so same thing. And we have multiple kernels. So kernel 1, kernel 2, and these are the weights, essentially. These are the things that are automatically learned in the network. Up to kernel K, and as output, we get, for each kernel, we get a new matrix, essentially. So this grid will be the output of, say, kernel 1. We would have, this one, the output of kernel 2, ... the output of kernel K. I messed up the 3D drawing over there. Okay, so, this could be called feature map K. So these outputs of the convolutions are called feature maps, and we'll see why they're called feature maps in a second. So feature map 1 per kernel. And so another word for feature map is activation map. They mean the same thing, and again, we'll see why feature and activation are used, but let's just define them as the same thing. So feature / activation map I, just index I, is formed by convolving kernel I across the image. So we essentially get many new images, one per feature extractor. And so we saw, before we could engineer a blur feature extractor, an edge feature extractor, a sharpen feature extractor. But CNNs are going to learn feature extractors that are highly specific to the thing you're trying to predict. And it might not be something that's interpretable. It might be some abstract concept that really helps with making the prediction, but humans can't put a word to. So in practice, images tend to not be black and white. So if the images are black and white, this is what a convolutional layer would look like. But recall that usually images are color. So I think we talked about this a few classes ago, but images are represented as RGB. And so I think we had an example similar to this before, but because we're going to talk about this so much, good to review it.
Don't they use another value in images now?
There's different subspaces, so you don't have to use RGB. There's other ones. And in color theory, the idea is that if you have 3 basis colors, you can take any linear combination of those 3 basis colors to form any color that you want. So RGB is a popular one, but other colors that together will form all the possible colors. It really doesn't quite matter because you can form any color as long as you have a good basis function. And so like in this example, we have a red channel, a green channel, and a blue channel, and 255, this is just for all of computer science, not specific to machine learning. 255 tends to be the maximum value given to any color channel, like in your monitor or on a website, etc. Just a convention, really. And so if we have the max value for R and B for these positions, we get purple, and we have 0 in all the other positions, that gives us black. We would get an image that looks like that. And this would be a highly pixelated image where it's only 6 pixels in the image. In practice, you have tens of thousands, hundreds of thousands of pixels in an image. So, okay, so that's just a quick review. So that means that, for color images, the process is a little bit, well, not too much worse. So, okay, 3D, I'm gonna draw a 3D box. Let's see how that goes. And so, the depth of this is 3, 1 for R, 1 for G, and 1 for B. So the depth dimension, which is this one, is equal to 3, and then we have width and height of the image as we always do. So in this case, we do a 3D convolution where our kernel is 3-dimensional, and we take the 3D dot product, but otherwise we basically do the same process. So we take the dot product between that kernel and that portion of the image, and then we slide it over, and then we do the dot product between this, the same kernel, but this portion of the image. Maybe I'll do dotted lines because you can't see what's going on back there. And that would correspond to the next pixel, etc. And we keep doing that, and we get our output feature map. So this red one is the upper left pixel. So that's basically it. And the takeaway for these convolutional layers are that the weights or parameters of the convolutional layers, unlike the dense layers that we learned about last time, are the kernels themselves. So we're trying to learn what features do we want to extract. And so after we have our activation maps, we can stack them to get our new image that's the start of the next layer. So we then stack the feature maps. And again, I'm using feature and activation map interchangeably because that's what's done. We stack the feature maps to get the input to the next layer. So, drawing that out, if we have our input, which is a 3 by width by height. Actually, let's just draw the dimensions down here. So the input might be a 3 by 32 by 32 image. And we have some kernels, which are 3D. Kernel 1. Being a little repetitive, but because this is such a central concept that we're going to see again and again, so it's worth being a little repetitive here. Let's say kernel 6 in this example network. So if we have 6 kernels, we're extracting 6 different features. Then we have dimension 6 for the number of features by, let's say, 3 times 5 by 5. So 5 by 5 kernel, 3 RGB, and 6 of those. So our filter layer is 6 by 3 by 5 by 5 for the filters. And as output, we'll get the result of applying the 5 by 5 convolution across the 32 by 32 image, which would give us a 28 by 28 image. And we have 6 of those. It gives us 28 by 28. There's the kernel starts inside the image, so there's only, there's minus 4 spots or minus 2 spots on each side because we start fully in the image. You could, yes.
Sorry, what's 5? Yeah, what is 5 by 5?
Yeah, it's just the kernel size, 5 by 5 by 3, which you can specify as a hyperparameter, by the way. So it doesn't have to be 5, but 5 could make sense.
So I understand the layers, like in this instance, like why is it 3D?
Because it's a RGB image. So we have our red channel, and this is just how images are represented in computers. Red channel.
That part.
So that's
Then
the
it's
by 3.
Okay, so then it's represented in 3 dimensions just to cover each of those parameters.
Yeah.
In that sense. Okay.
Yeah. So that
Okay.
basically we're
Okay.
incorporating the color information into the prediction.
Okay.
So like instead of RGB, we use like the hexadecimal code, it would be like 6 dimensions?
Yeah, the hex codes are typically RGB.
Okay.
I mean, it's like 255, 255, 255. Each of those 255 numbers could also be represented as a 2-digit hex number, and you have 3 of those 2-digit hex numbers, which have 255 degrees of freedom each, and that gives you a 6-digit hex. So it's just different ways of encoding the same information.
Does the word kernel and filter, are those synonymous?
Yes, yeah, so kernel, filter, same thing. Activation map, feature map, same thing. Yeah, just terminology that people use. Let me write that explicitly in these notes. Filter equals kernel and feature map equals activation map. Same thing.
Then each kernel is obviously smaller because it's going to be moved around.
Yeah, it's basically trying to extract features from each portion of the image. But you can play around with how
Yeah,
big you want.
sizes, and, yeah.
And so, yeah, this will result in a 6 by 28 by 28 output map, which, just to be clear, is 6 maps, which are each 1 by 28 by 28, and they're 1 because we take the dot product, that gives us a single number, and we get that across the image, so 28 by 28. But we have 6 different kernels, so 6 of them. Yep, so that's one convolutional layer. So convolutional neural network, a CNN, starts with, I shouldn't say is, starts with several convolutional layers, and we'll talk about why, in addition to the reasons why we like deep learning that we talked about last class. There's a few image-specific reasons. So, input image, which has a set of kernels or filters, which results in a activation map, which, if we have a lot of filters, will have a higher depth than the input image, most likely. So a deeper cube, I guess. And then that activation map can be thought of as the input to the next convolutional layer. So there's more kernels with different weights that are applied to that activation map to generate the next activation map. And we keep going for several layers. We'll talk about why right now. So that's the beginning part of a CNN. Yes?
Why does the cube get bigger in any direction? Shouldn't it just be extended in one and get it a little smaller?
Yeah, it should get smaller. I just messed up in how I drew that. Yeah, sorry, thanks. So just to be fully accurate, that's good. Let me get some more space. So technically, as we saw before when we went from 32 to 28, it gets smaller each time. In fact, we'll apply another kind of layer later that'll make it get even smaller. We'll see that today. So the main reason that you like to do these multiple layers, in addition to, remember last time we talked about deep learning is good because it allows us to learn more complex functions with less weight, so it's just good from an efficiency standpoint as opposed to just one layer. But in convolutional networks, applying many features per layer and then adding multiple layers allows us to have, because of exactly what was said, where it gets smaller each time in the width by height dimension, each kernel, if it's the same size, represents a larger portion of the input image as you go deeper into the network. And so the effect of that is that as we go deeper, each filter is able to extract higher level concepts from the image. Let me break that down, but that's basically the answer. So in order to learn, and to help do that, we introduce a new type of layer. So in order to learn higher level, and by here higher level, I mean abstract more abstract representations, we can downsample, and this is pretty common practice. Downsample the image, or sorry, I guess I should say feature maps at each layer to extract the most salient information. So that's a lot of words. Let's break that apart, and maybe the easiest way is to introduce the next type of layer. And this is called max pooling layers that are another kind of central part of a CNN. And so max pooling is much simpler than convolutional layers. Easiest way to understand it is just to see an example, I think, than to define it. This is one of those examples where defining a mathematical function to explain this would look really complex, and just see an example, it's like super simple. So let's say we have a activation map, and
What's that word? The most salient information?
yeah, most salient.
Okay.
3049, -1003. I'm just making up these numbers. Doesn't.
So is this what you're writing now a feature map or?
Yeah. So feature map example. So what we do in max pooling is we look at windows just like we did with convolutional layers, and we take the max of each of those windows. So in this small example, we might look at these windows. So 4 different windows, and in each of the windows, we get the largest number in that portion of the image or feature map, which can be visualized. In this case, max of 3049 is 9. Max of -1003 is 3. Max of the red part is 7, and max of the purple part is 4. Let me just draw.
What happens if you don't want the dimensions reduced that much?
So in practice, you do, but if you don't want them to, so the question is, what if we don't want to reduce the dimensions per layer? Then you just don't add max pooling layers. But in practice, max pooling out to be highly useful because we'll talk about that now.
So when you're running the other, does that also reduce the dimensions?
It does slightly. We saw this example here where the dimensions went from 32 by 32 to 28 by 28. There's a hyperparameter, which we'll talk about in a second, that can prevent that from happening. So we'll talk about that.
I have a question.
Yes.
Are we losing information if we just like pick out like I guess the highest value in each of those?
Sorry?
So, if I understand this correctly, we're like picking out like the maximum values,
Mhm.
but aren't we losing information when we do that?
Yeah.
So what is the advantage of? So I guess it's like, I guess it's a cost of computation versus how much information you want to keep.
Well, it's that. So the question is, why do we do this? Because we're losing information, and it was brought up that maybe it's to save computation. That is part of it, saving computation. But the bigger reason is that, we're going to talk about that in a second. But yeah, keep that question in mind because I'm about to answer that. But first, let me just write in words this process. So we take the max element in an n by n, in parentheses by n in case it's 3D window. Okay. So the effect of this, and this is to answer your question, the effect of this process is that each pixel in progressive layers represents a larger portion of the original image. This is at least the first half of the answer. So for example, let's say that we have this input image of, input image, and let's say it is Stella, it's the input, and yeah, this looks kind of creepy actually, but let's pretend this was a cute dog and not a creepy looking thing. And so, the earlier layers of the network are learning to extract features like edges or curves or really small things that might appear in a 3x3 portion of an image, like really small features per grid. And then as you downsample and go into further layers, well, first let's write this down. So earlier feature maps extract low level features. And then as we go further, we get slightly less level features. So for example, we might, let's call this mid-level features. Things like maybe the side of the head, or the edge of an ear, or a portion of an eyeball, or part of a neck, or a small portion of the smile, or some parts of the whiskers, or another portion of the eyeball, or another part of the head, other higher level things that it's looking for to make the classification, other things. And then as we go even further in the network towards the end of the convolutional portion of the CNN, then we get, as you might have guessed, really high level features. High level features where it's looking for things like, what's the general shape of the head? Is there a general head shape like this? Are we finding an ear that's out? Because each kernel is representing a large portion of the original input image because you keep downsampling. Is there a muzzle? Is there a, that part of the eye? And you could get features that are looking for different things for different kinds of dogs. So maybe some dogs have a lot of fur and some dogs don't have much fur, etc. So, maybe some are frowning, some are smiling. But so as we go further in the network by having each basically what I just said, by having each kernel, let's say it's still 5x5, now each 5x5 portion of the feature map represents a much larger corresponding portion of the original input image. So by downsampling, we're able to make the neural network learn progressively higher level features to extract as we go through the network. So that's the main reason that we apply max pooling, is that it makes it really easy for the network to learn different levels. It has some features that are extracting really small details and other features that are extracting really high level things about the image, which is kind of cool actually, because you can imagine how this is the beginning of many other, well, you will see eventually, I guess.
Is this how CAPTCHA works?
CAPTCHA? So CAPTCHA is a way to get training data. So it's basically like people, it's crowdsourced. We'll talk about it later. Yeah, sorry.
How many layer is sufficient for example, extract those different features?
Sorry, what was the question?
How many layers is sufficient?
How many layers is sufficient? So so the thing about deep learning, unlike some of the older school machine learning, there's no mathematical proof to this stuff. It's all like try it out and see what works. Like that's the state of the art of deep learning, is try it out, see what works. If it doesn't work, try something else. So there's ones that people have tried that tend to work really well, but it heavily depends on the input dimensionality of your data, how many input images you have, how complex your images are. It's highly data dependent, just like the first part of this class, which model to use. So yeah, there's no one architecture that works optimally for every data set. And in general in this class, there's no machine learning method that works the best for every type of data set. If there was, then there wouldn't be much to learn in data science. You just use one thing and you're done. But because that's not the way it works, I mean, maybe one day we'll get there, but right now, as of today, there's no one best model per data set, which is fun, I guess, or frustrating, but probably fun. So now we know all the components of a convolutional neural network. So putting it all together, a full CNN, or we could call it a prototypical CNN. I think that's the right word. Prototypical CNN consists of, you have your input image, and that goes into a convolutional layer, which goes into a max pooling layer, which goes into a we learned about last class that actually make predictions really well. And that gives us our output prediction. And we repeat this archetype many times. So convolutional layer followed by max pooling layer. We repeat that multiple times, and it's repeated a different number of times for different architectures. And then after that, we might have a few dense layers. So the dense layer can be repeated multiple times as well. And so we basically stack these layers progressively to do what we want. And what's interesting is that, well, it's all interesting, but an interesting thing is that this first part of the network has a goal, and that's to do the automatic feature extraction. So you have the beginning part of your neural network that's extracting visual features, and again, progressively higher level features. And then you have your last part of the network that is basically logistic regression on steroids, but what we talked about last class, a lot of a neural network for prediction. So this would be the MLP network from last class. And because we have one layer after another, like we talked about in last class, the output of this automatic feature extraction step is basically the input into this prediction step. So the output in practice, the output from feature extraction is is input into predictor.
Sorry, could you go back up?
Yes.
So does step 2 and 3, like the convolution layer, the max pooling layer, you put that as repeat multiple times. So do those two like kind of go in a circle, and then after a number of times we go to the next? Does that say dense?
Dense, yeah. Yeah, so you might have max pooling, convolutional max pooling, convolutional max pooling, then dense. Sometimes you have convolutional pooling, or sometimes you have multiple convolutional layers. So maybe, you could always modify this, but you could also just repeat the convolutional part multiple times before you downsample. That has worked well in some cases. And all of this is trained with gradient descent, just like a normal neural network, and has backpropagation, just like we talked about. Basically exact same concept, just with these convolutional layers and max pooling layers, where the weights are from the convolutional kernels. So it's same concept as last time, just we have a new type of weights. They're not these weights of nodes connected to every node. The weights in these layers are the kernels. And that's what's automatically learned during the gradient descent process. Okay, so that's the basics of a CNN. So now I want to talk about some common hyperparameters in CNNs. And we'll introduce a few new concepts. So common hyperparameters in CNNs. So in a dense, and let's break it down by layer. So first we have dense layers, which we learned about last class. And the two hyperparameters are the number of nodes in the layer and the number of layers. Basically, actually, not number of layers, because we're saying for one layer, these are the hyperparameters. But yes, also, you can design the architecture to have multiple layers, but that's not a hyperparameter. But another hyperparameter is the nonlinear activation function you want to use. Last time we learned about ReLU. Oh, I should say that sometimes ReLU often is applied to the output of the convolutional layers. So just like before, we do this nonlinear activation function. So that's dense layers, what we talked about last time. You can choose the number of nodes in your layer and which activation function you want to use, so that your network's not just learning a linear separating boundary, but potentially any function that exists. These are universal function approximators, given enough nodes and layers, as we talked about last time. So the convolutional layers have some hyperparameters as well. Of course, the number of kernels. So how many kernels do you want per layer? What do you want the kernel size to be? We chose 5 by 5 here as an example, but 3 by 3 is more common, and really you can change it around. Another hyperparameter that we haven't talked about is called padding, and this is going to answer that question that was brought up of what if you don't want the dimension size to change in progressive layers? Yes?
Is the number of nodes of the first dense layer given?
So technically, I mean, if you're thinking about the input to a model, but that's kind of just like an implementation detail rather than a conceptual. Like in TensorFlow, yes, but in like math thinking, not really.
Calculate that. Remember that somewhere.
Yeah, and in implementation, you call your input layer a dense layer, and so there's an input, yeah. But actually, that's different. That's not really a hyperparameter. That's like the input to your model, and then you also specify in that layer.
After the convolutions.
Oh, after the convolutions.
Because like the first dense layer needs to be the same size as the output.
Oh, I see. Yeah, so the question was, when you're going between convolutional layers and dense layers, how do you do you get to specify how many nodes are in that dense layer? The answer is yes, because what happens is once you get to here, you will do something called flattening your activation map. So, your activation map there will be, this 3D grid. And so then you flatten it into a 1D vector so that could be input into the next dense layer. Yeah, that's a good point. The tensor that happens right around there. That makes sense, because dense layers need a 1D vector as input, but the convolutional layer doesn't output a 1D thing, so we just make it 1D by flattening it. Okay, so padding is the solution to what happens if you don't want the dimension size to change. So what we do in padding is, let's say this is the image or the feature map. We can add zeros around it so that, and you can specify how many layers of zeros you want, such that when you have your kernel slide, it starts around these zeros that are padded, and the zeros don't really have an effect on anything because they're empty. But if you convolve and go through the network like so, then if you have enough pads, you can ensure that the output dimension is the same as the input dimension. Let's help sure that output dimension equals input dimension. So that's optional. And then another hyperparameter is something called stride, which is how much to move the filter.
Will you give an example of this? Like,
Of what?
of padding? Like, what, I guess, yeah, I'm just not sure what it would look like.
Oh, it's the exact same as before. It's just the same as convolving as before, but now you just have zeros around the image. So nothing else changes about the process.
Oh, okay, so, okay.
You're just padding the image with zeros so that if you convolve, the output dimension will be the same as the input. And the zeros don't have an effect on anything. And then stride also has to do with filters. It just tells us how much to move the filter. So instead of moving it 1 each time, we can move it by more than 1. Oh, forgot to draw this. Let's say this is the top part of an image. Probably didn't need to draw this many vertical lines, but that's okay. So if we start here, instead of moving 1 over, we might then go here. And in this example, stride is equal to 2. So like red is step 1, green is step 2, etc. We just keep going. You might use stride if you know, as another way to downsample your next layer. Yeah, I mean, that's basically it. So that's another common one. So those are the common hyperparameters for convolutional layers. And then finally for pooling layers, you can do window size, just like with convolutional layers. Just it's called a window instead of a kernel. The window size, same padding and stride. So very similar hyperparameters as to the convolutional layer. Okay, so that is convolutional neural networks for you. Any questions? Okay, so now we're going to talk about how convolutional neural networks are used in practice. Yes, question?
Do they only use for, I was gonna ask, do they only use for images? But I think maybe getting to that.
Are they only, sorry, what?
Only used for images?
No, they're not only used for images. They were originally used for images, and so convolutional neural networks have resulted in state-of-the-art performance for image recognition. So if you're gonna classify images, you probably wanna use a CNN, but they also are used for other things like DNA prediction and sound prediction, and yeah, we'll talk about those. So the next concept is called transfer learning, which is the beginning of a very exciting series of topics. Transfer learning. Has anyone heard the term transfer learning before? Okay, relatively new, but a few people have heard it. Okay, good. So transfer learning is basically one of the keys to what made convolutional neural networks perform so well, like orders of magnitude. Okay, that's an exaggeration, but like really, really well, way better than any other type of image recognition model. And the key idea of transfer learning is that many lower level features can be reused for a variety of purposes. So, example, I think this concept's actually not too hard to understand once you understand how a CNN works. So let's just go straight into an example. So let's say that we want to train a CNN to predict cat versus dog. And so the feature maps that it may learn, for example, might be, we might learn these lines and curves as we talked about earlier, like really 3x3 pixel or 5x5 pixel concepts. Like the first layer might learn things like that, and if we go into the second layer, it will learn, let's say we added max pooling between these, it might learn slightly more abstract, but not too abstract. So maybe starting to look at like the side of a head, the edge of an ear, but like visual patterns that can be applied to a variety of different things. These are not like specific to cats and dogs. Like you might see lines and images of cancer lesions, or in hot dog versus no hot dog, or whatever example you're going with. And so that's really the key observation of transfer learning, is that the above features are useful to many prediction tasks besides cat versus dog. And this concept is the start of why deep learning just is way better than other models for big data. So that's the key observation. And it's a two-step process. So the steps of transfer learning are step one, we pre-train, so new vocabulary word. Instead of train, we're gonna say pre-train, which is really the same process, but we're pre-training a CNN on a data set that's not the data set of what we want to predict. So we're just doing the regular training process, but because it's not the final thing we want to predict, we're calling it pre-training. It's a common vocab word, so I'll underline it. And then step two is that we will freeze, another vocab word, freeze the weights of the first n convolutional plus max pooling, even though there's not really weights there, convolutional layers, and only train, well, maybe I can make that and a third step. And then step three is to train, and this is the transfer learning, so AKA transfer learn. The remaining weights on the data set of interest. So maybe I should clarify that this step one can be any data set, although the closer that pre-training data set is to the final task, the better it does, but we'll get to that later. So for example, image, convolutional layer. Oh, you're gonna start seeing in this class as we get higher level, we're just gonna draw things at a higher level. So like, hopefully it's clear what's going on in this picture. Image, convolution, convolutional layer. This is like how people actually draw it though. Because like these concepts are repeated, and as I said, building neural networks starts to be like Legos, and so it's worth abstracting it. Prediction, so yeah, that's just a CNN. So in transfer learning, we keep some number of these weights fixed. So during gradient descent, we keep these weights fixed during gradient descent. And during gradient descent, we only update these weights. Only update these weights during gradient descent. And the benefit of this is that multiple benefits. One, you're training much fewer parameters because all those parameters at the beginning were already trained. Second benefit is that if some person with a giant data set like Google comes along and trains a data set of, say, 15 million images of just common everyday objects, and then gives you that model with the weights that are pre-trained, and then you want to learn for a highly specific task, like let's say, hypothetically speaking, you're a medical AI researcher and you want to classify cancer versus not cancer, and you have a few thousand images, you can take all that learning of general feature extraction from that millions data set that Google did for you and has conveniently released for free, and And transfer learn frees all the weights, and you're only training these last few weights, which requires much fewer images to train because there's much fewer parameters to learn. And now you get state-of-the-art performance because you have this general purpose feature extractor that's really good that's been given to you. So that's kind of the power of transfer learning. It also lets you do things like train a model for a while, save the model weights, give it to your friend, and have them train it on more data. Allows you to do things like train data on, okay, this is getting really human-centered AI stuff, but like train it on a private data set, then save the model weights, give that model to someone else that you continue training, and you didn't share the data, but you shared what was learned by the model and you continued off there. Things like that, we'll talk more about that in all those human-centered classes that I'm teaching in the future. So if you like that kind of stuff, stay tuned, but not in this class. So sorry, I get carried away because I really like this stuff. But an important thing to know about is that the most common pre-training data set that's used for this, and you probably, if you've done computer vision, you definitely have heard this, is called ImageNet. Who's heard of ImageNet before? Okay, so ImageNet is not a network, it's a data set. I know sometimes people get that confused because the name makes it sound like it's a network, but no, it's a data set. It's a data set that has over 14 million images. And I'm giving a very specific example because it's so common practice to start with ImageNet weights that it's worth knowing about. Because probably if you're doing computer vision, you're going to start with ImageNet pre-trained convolutional neural networks. So it's over 14 million images, over 20,000 classes that it was trained on. Or sorry, the data set consists of over 20,000 classes, and each class is a common object like a chair, remote control, grasshopper, etc. 20,000 of those, and hundreds of images for each of those 20,000 objects. It's a very general purpose data set. So if you pre-train on that, you have a model that's learning to distinguish all sorts of things, and probably it's generalizable to whatever specific thing you're really interested in predicting. So many CNN architectures, I think it's maybe better to just define these in context rather than writing a definition. So many CNN architectures are pre-trained on ImageNet, and they are readily and freely available. So like for your final projects, if you're implementing something in TensorFlow, Keras, say, which we will get practice on next class. Next class is a coding class, by the way, so we'll learn the libraries for coding neural networks. You might start with a CNN pre-trained on ImageNet and transfer learn on that. Yes, question?
ImageNet only for classification?
So ImageNet is just a data set, and it has all these images and their classes. So when it's pre-trained usually as a supervised learning task. But there have been papers that have been released that do like unsupervised learning with ImageNet that basically discards the labels. And so I don't know if that's what you're talking about. Or are you saying, can you take a model with Oh, yes, and we'll talk about all that stuff, including one of the notebooks in next class is on segmentation. So we'll get there. We'll get there really soon of like all these things besides prediction that neural networks allow us to do. It doesn't stop at prediction, which is really cool. And the big hint of that is ChatGPT. That's not prediction, really. That's something else. But there's a lot of things along the way that are also cool that we're going to learn about really soon. So let's just write that note, that long tangent I said, that starting with ImageNet weights is common practice. just so you have that in your notes. I don't know if I want to write all this out, but transfer learning enables deep learning with small data sets. So if you want to do deep learning but you have a small data set, you want to use transfer learning. If you want to get reusable feature extractors, transfer learning. And if you want to continue training where others left off, then transfer learning. So very powerful, highly used today concept. So we're getting into the 2010s now of machine learning. And so actually, speaking of all the other things that neural networks can do, besides prediction, let's get into that now. So new section, I don't want to write so much. So DL, deep learning, enables way more than just supervised learning. And this is why neural networks have really taken off. They get on big data, they get state-of-the-art prediction performance. So on supervised learning, if you have a big data set, or if you have a small data set and you're doing transfer learning, they're the best there is. Unless you have really simplistic data like that's in Excel, then you should use all that stuff from the first part of class. Like if you're working with Excel tables, probably don't use deep learning. But if you're working with images or sound or text or highly complex data, deep learning. Okay, so first class example of things that deep learning enables more than just supervised learning. So first class example of many. And this is going to be a concept that we've already learned about, but now we're going to learn how deep learning does it. So dimensionality reduction. Dimensionality reduction with neural networks. And hopefully when you do problem 4 in the homework, you're like, I like this one better because it's much more conceptually understandable. So the idea of a dimensionality reduction, as you know, we'd have high dimensional input data, and we want to reduce the dimensions. And so the way we can tackle that with a neural network is as follows. I'm going to set up a very specific type of dense neural network here. So we have that input layer, which goes into that input layer, which goes into that input layer, which goes into this larger input layer. So why am I saying input? So this next layer, which then goes into this output. The input to the model is the data, so X, that goes into the model, and the output that the network is trained to predict is X. And so the idea is that we train this neural network with backpropagation, with gradient descent, as we always do, but instead of trying to predict f of x, to predict y, try to predict a label for x, we're trying to make the network predict x itself. So the input to the model is x, the output to the model is x. So you're probably like, okay, well, what's so fancy about that? It just doesn't need to change anything, and you'll get that. But notice the network architecture. In order to get to that last layer, it has to go through this tiny layer in the middle in order to get to the output layer. So somehow the information is able to flow into a small number of nodes in this middle layer, which then flows into progressively larger layers. And so the information has to go through a bottleneck to get to the output. And so you're going to lose some information because you're reducing it has to go through this small layer with with only a small number of nodes. But if you train this model now to do something called reconstruction loss, so a new type of loss function called reconstruction loss, which is exactly what it sounds like, just how similar is X train.
So what is each line going to represent?
Wait 1 second. So, for example, we might use the same loss function that we were using before, like cross entropy loss, like we use for logistic regression. But instead of between X and Y, we do that between X train and X train. So instead of cross entropy between X train and Y train, like in logistic regression, cross entropy between X train and X train. Okay, so the question was, what do each of these layers represent? It could be any type of neural network, but what I'm trying to draw here are dense layers. So these are all the dense layers that we learned about last class, and just with a smaller number of nodes per layer. So for example, maybe let me do a concrete example if this would help. So let's say our input is I'm going to do a small example. Let's say our input is a 5-dimensional vector, and we want to create a feature extractor that can, a dimensionality reducer, encoder, if you will, that will, that's only 2 dimensions, that reduces the dimension from 5 dimensions to 2 dimensions. So if you force the data to go through only these 2 nodes in the middle, you're going to get the reduced data. And so when you have an autoencoder, this is called an autoencoder, then this first half of the network is called the encoder. Makes sense. Encoder. And the second half of the network is called the decoder. And this middle layer is the compressed data. So like instead of using .zip, you could use a autoencoder. Although .zip's pretty good. Sorry, any questions? Is this intuitive or is this like not making sense?
I'm sorry, it's still compressed what?
Compressed data. Yes.
Quick question. Maybe this is a weird question, but on like a high level, what's the difference on a data set between this and like a binary decision tree? Just with the example of using a 2-dimensionality, would that be like a similar for this one that if you change the dimensionality, would just be looking elsewhere, or does that question make sense?
I mean, I like the creative thinking, but I'm struggling to see. So like the point of this is dimensionality, like reduce the dimension. Binary decision trees like to.
Because I'm just wondering, just in the example you drew, since it's only 2, we don't necessarily know what's activating each one of those nodes, right? We know what the activation function we've given it is, but in this case, wouldn't it be, I'm just wondering, and would it be more similar to say, in this case, is input 1 active, yes or no? That's your dimensionality down 4, it either goes to one of the nodes and then therefore gives you your output, or is that trying to think too much into what's going on within the node?
So you're saying like, if you like for the first node, it's kind of there's a weight times each of the inputs, and so is it like a binary? I don't know. That's confusing to me. I'm sorry.
No.
That's maybe it is, but it's not commonly thought of that way. But I could see the similar. I mean, you do have a network and you have nodes and edges like a binary decision tree, and what you do with each of the nodes and edges is a little different than what you do with a but it is, I guess, analogous. It looks similar, so I guess it's similar in that way. Any other questions?
Sure. If you were in like a scenario where you couldn't transfer like large data sets, could a data set then be like encoded down, sent, and then decoded back?
Yeah, I think it has been used for compression in some ways. So yeah, I think this is like a way to do compression. It's not, it's noisy and you're not guaranteed to
Got it.
fully reconstruct it, but yeah, it is used for that. And yeah, this is kind of the first thing. This is kind of the precursor to like deep fakes too, by the way. But we'll get there. Okay, so I guess, yeah, on that note, so just to be super explicit, to encode data, so to encode data, we would take the input and pass it through so we train the autoencoder and then we chop off just the encoder part and we put the input through just that pre-trained encoder portion of the autoencoder and we get our encoded data. And similarly to decode data, just the opposite, we chop off the second half of the network. So we train it as an autoencoder. Once you've trained it, you can just take the first few layers and not put it to the next layer, but just take the output. That's basically what we're doing. So to decode data, and hopefully you're starting to see where this Lego block like analogy to neural networks comes in. We're literally chopping off the network and using different parts for different things. Which I think is one of the things that makes this really fun. So we take our input decoded. Some of the highly theoretical people get mad when I talk about it that way, but I still see it that way. So we have our decoded data and just emphasizing that we're using saved model weights. So we've already trained the model and we're using the weights. After we've trained the model, we use the learned weights to do the encoding and decoding. So this is where machine learning starts to get really fun because it starts to get kind of creative like this, where like, imagine inventing this. There's no like really mathematical, proving of anything. You're just like, what if I kind of, take it off here and have it output there? What would happen? A little bit more than that, but basically that's the kind of thinking that starts to go on. And then that's how we eventually, that type of thinking is what got us to ChatGPT. So that's why I think it's fun. So last note is that it doesn't have to be dense. So if you're doing an autoencoder, you can use an convolutional autoencoder as well. So convolutional autoencoders work well with image data and are commonly used. So same idea, except with convolutional layers. You have your image and your convolutional layers, and then you might flatten that, and then you do a type of upsampling, which we'll talk about more later, like how do you upsample convolutional layers. And then we get a reconstructed image, and same thing, we do this reconstruction loss, but now it's a same thing, cross entropy between each of the pixels in the image versus each item in a vector, same thing. You could flatten it and think of it as one large 1D vector, but same idea. You take an input image, you train it to get through smaller layers and then larger layers, and your loss function is predict the input image, but make it go through this bottleneck where it's really small. And so the information has to flow through that really small layer. And that's how you can compress image data. And it's also the basis for many other things, which we'll talk about next week, because on Thursday we're going to start coding neural networks. So bring your laptops and get ready to, actually, so I already posted the notebooks for you, so we're going to go over solutions. So if you have time, work through it. Otherwise, yeah, we'll go through it anyways. All right, see y'all on Thursday.